Hello, everyone. My name is Mascaran, and in this video, we are going to continue our discussions on curve mirrors. So this is part three of a four-part video series. And in part one, we discussed some of the intro and motivation and some of the design trade-offs for current mirrors. In part two, we talked about a few different topologies of current mirrors, around four or five topologies for mirrors. And in part three, which is this part, we are going to initially discuss the systematic mismatches in current mirrors. And then majority of this video, though, would be discussing random mismatch in current mirrors, and we will discuss about Pelgrom's law as well. In part four, we will continue our discussion with Pelgrim's Law, and we will also, discuss the layout consideration for converters. All right, so let's start with the part three content. First, we are going to discuss the systematic mismatch. So when you have a current mirror, in a basic two transistor current mirror, we said that the VDS1 and VDS2 may not be equal, and then we introduced a cascade current mirror where we add two additional transistors on top of the actual current mirror. And the one of the things that these two transistors, these two upper cascade transistors do is that we design them in a way such that the VDS for the current mirror transistors remain the same or nearly equal, right? But if it's not equal, that's one of the things that causes systematic mismatch. One other thing that we didn't talk about is the body effect. So in our part two, we completely ignored the fact that some of these transistors may not be at equivalent source to body potential. And so if VSB1 and VSB2 are not equal, or VSB in general is not equal in the transistors of a current mirror, then that will also cause a systematic mismatch. Again, one other thing would be the aspect ratio of transistors. So even though the W by L ratio of the two transistors equal, if the length is not equal of both transistors, so L1 is not equal to L2, or W1 is not equal to W2, that will also introduce a systematic mismatch in a mirror. And lastly, systematic mismatch is also caused by poor layout. Uh, we will talk about some of the layout practices and some of the layout considerations for current mirrors, to suppress some of these systematic mismatches, but that will be pretty much in the end of part four. All right, so now let's talk about random mismatch. So before I go on with some of the discussion, I would like to point you to a very good resource, in my opinion. So there's Dr. Ali Sheikholeslami from University of Toronto, and he has a great article series. It's called Circuit Intuitions. And so maybe after you watch this video, I want you to go and look at article number 4. And I have the link here in my notes, and I will also post this link somewhere in the description of the video. If you're watching this, you'll find the link to this article 4. And I suggest you watch it because it's about random mismatches in current mirrors, and I think it's a great resource, very concise and to the point. All right. So to kick off our discussion about random mismatch in current mirrors, let's first talk about the drain current equation of a transistor when it's in saturation. So that's this equation, and we have seen it a million times, right? But let me just rewrite this equation in terms of beta, where beta is mu n C ox, W by L, right? And the overdrive voltage squared divided by 2. So one of the things, there's two things in current mirrors that are, that are a major cause of random mismatch. One is the beta. Second is the threshold voltage. And there's others too, but for now, we will, in this part, we'll discuss about the threshold voltage and the beta of the transistors. And as we will see that, there is variations in both the threshold voltage and the beta of the transistors. And so where this video will eventually go is that, we have these transistors in current mirrors, and if all of these transistors don't have the same threshold voltage or the same beta, these are assumptions that we made before to, sort of think that we will have an accurate current. But now we're going to discuss how these threshold voltages and the beta of the transistors may not be equal. And there's going to be some sort of variation, which will cause an error in our current meters. And so that's all this video is about. And while we'll discuss that, Pelgrom's law is going to be a big topic. But for now, let's start with a hypothetical question. So let's assume you're in a foundry and you're tasked with you have a chip that has 100 transistors, okay? And these are 100 identical transistors that are adjacent, placed close to each other, and again, like these are absolutely identical in terms of biasing, sizing, layout, all kinds of different things. Like assume that the conditions of each individual 100 transistors is the same. All right. And now the question is, will the threshold voltage of these 100 transistors be the exact same under the same biasing conditions, if the sizes are the same and all these different conditions for a transistor are the same? Will the threshold voltage be the exact same? And the answer is no, right? We will see in practice after the chip is fabricated, and let's say you're measuring your 100 transistors, you're going on measuring VT1 of the first transistor, the VT2 of the second transistor, and threshold voltage of the third transistor, and so on. You'll find that it could be something like this, where let's say this is the mean value of VT, right? So this is, let's call it mean of threshold voltage. And you might find that there is a distribution of VT. So most of the transistors might be close to the mean value of the threshold voltage, but there could be transistors that have a little bit of higher VT, that might have a little bit of a lower VT, and you'll also have some transistors that are a bit further away from the mean of VT, and yeah. So basically, you'll have, the point is that you'll have some sort of distribution in your threshold voltage. So all of these 100 transistors in our hypothetical example will not have the exact same threshold voltage. It will be some sort of a distribution. And so let's think about how that affects our discussion about current mirrors. So previously, we talked about a two transistor current mirror, the simplest mirror possible. And, we came up with this equation where it's a ratio of beta 1, beta 2. And, it's also a ratio of override voltages of both M1 and M2. So now, previously, if you look at part 1 of this series, we said, okay, well, if VGS1 is equal to VGS2 and threshold voltage is VTN1 is equal to VTN2, then we can pretty much cancel out this term, right? That's what we did for part 1 of the series. But now we are saying that VTN1 and VTN2 may not be equal, because there is a variation in, just like we said, if you have multiple transistors, like even identical, they'll have some sort of variation in threshold voltage. So chances are when you fabricate this current mirror, maybe the M1 and M2 will have or might have different threshold voltages. And so even if it's slightly different, you can't really cancel out the overdrive voltages like we did in an ideal case, right? And so that's so in a way, this term, because now we're talking about variation and we're saying that these terms cannot be canceled out, this is an error term, right? This is an error term which is caused because of the random mismatch between VTN1 and VTN2. And I could say the same thing for beta 1 and beta 2. It's pretty much along this, the discussion is pretty much along the same lines, that the beta 1 and beta 2 will also have some variation. And so if you have two transistors, they might not have the exact same beta 1 and beta 2, which will also introduce an error, right? So now let's think about, if you have this current mirror, okay, and let's say you have copied it and placed it in multiple different parts of a chip, right? So that's what I've shown here on the right. You have a chip and you have the same mirror, and you have, you have copied it and you have placed it like in different parts of your chip. And let's say, for the sake of an example, this I out, you designed it to be 20 milliamps. Well, now let's think about it. If M1 and M2, we talked about like the threshold voltages having some sort of variation, right? So M1 and M2 threshold voltages might be different. So it will introduce, let's say, a particular error. Now, let's say this was this mirror, but this mirror would have an other M1 and M2, and the error between those, the mismatch in VT for that mirror might be different from the first one. And so let's say you might find like this mirror draws, for the sake of an example, instead of 20 milliamps, it draws 20.1 milliamps. Here, the error might be different, and you might see 20.099 milliamps or something. And so on. The error might be different for this mirror and this mirror and this mirror and this mirror. So the point is that there will be some variation because there is a variation in the threshold voltages. There will be some error in the mirroring action of a single mirror. And that error will be different if you have multiple different copies of the mirror itself on a chip, right? So point is that because of this threshold voltage variation, you will have a distribution in terms of the output current of the mirror as well. So in other words, if you have 100 mirrors, 1,000 mirrors, all of them would not sync or source the exact same I out. It would be some sort of variation. Most of the mirrors might be drawing something very close to I out, but then there might be other mirrors which are a little bit farther off from the mean value of I out. So that's to give you some sort of an idea of like how these random mismatches will affect our current mirror. So let's talk about Pelgrom's law. And let's start with the equation of a transistor, the drain current of a transistor in saturation. So again, we have seen this equation before. Just a side note though, for neural processes, the drain current of the transistor is not really a square law relationship with the overdrive voltage. So these days it's more like a linear relationship. And okay, so anyway, what I was going to say is in this equation, let's treat mu n C ox W by L, which is, in other words, beta. So let's treat beta and the threshold voltage, which is VT, as random variables. So let me say RV. So now we're not thinking of VT and this beta as like, a variable that has a particular value. We're treating these two variables, beta and VT, as random variables. So now I'm going to say something that is pretty much the most important part of this video. So Pelgrom et al. Paper from 1989, what they said in their paper is that the variance of the threshold voltage of transistors that are adjacent and identical, the variance of those transistors like that would reduce inversely with the gate area. So again, the variance of the threshold voltages of transistors that are adjacent and identical would reduce inversely with the gate area. And the gate area is this. It's just a product of length and width. So that's, again, a mouthful, but this term is the variance of VT. Variance of the threshold voltage. And that's this term, okay? And the gate area is this term. And this term, AVT squared, is just a constant. Just some constant, okay? So now, basically what Pelgrom's law says is that if you increase WL, you increase this product of length and width, or you increase the gate area, then the variance in your threshold voltage would decrease. All right, so again, let's talk about some things. If VT1 and VT2 of two transistors, let's say, These are random variables. Let me point this out. So the difference in VT1 and VT2 would be delta VT. That's also a random variable, by the way. So the variance in delta VT is equal to the variance in threshold voltage of transistor 1 plus the variance in VT of transistor 2. And that is equal to, again, what we saw from the Pelgrim's law, AVT squared divided by the gate area. Okay, and this equation holds for like two transistors that are, if VT1 and VT2 are identical and independent as random variables. Okay, just a bit of side note here. Standard deviation is just square root of variation. So if this is the variation, sorry, if this is the variation, then the square root of that, this is the representation of the standard deviation of a threshold voltage. Okay, so let's look at an example. Let's look at an example, and basically we're thinking of how does the standard deviation of the threshold voltage, which is sigma VT, how does it change if we modify the widths of identical and closely placed transistors or adjacent transistors, if we make the widths 4 times bigger, okay? So we go from W to 4W. How will the standard deviation of the threshold voltage change? Okay, so let's write down some equations from Pelgrim's law, right? We said that the variation in the threshold voltage, let's say delta VT prime, would be A VT squared. And now we said instead of WL, it would be 4WL because we have increased the length, increased the width by 4 times. Okay. And the standard deviation is just the square root. So that would be A VT over 2, sorry, 2WL. Okay. And this term is equal to this, the standard deviation that was there before we, quadrupled the bit. So we can write it as delta, the standard deviation of delta VT prime is half of the original one. So sigma delta VT, that's the original one. And now the standard deviation is half. So we made our width 4 times and our standard deviation became half. So what does that signify? Let me just write this down as well, just so that it's in the notes. Standard deviation of VT, threshold voltage is halved if W goes to 4W. Okay, and so like looking at a graph, it might look something like this. Let's say this was original W by L gate area, right? And then in this example, we said, well, okay, let's make width 4 times. So the gate area now becomes 4W into L. Now that's the gate area. So that's the curve in blue. And so what we are trying to show here is that because the standard deviation decreased, that means more of the values, more transistors have their threshold voltage closer to the mean. In other words, you have made a tighter distribution by increasing the gate area. So you're more likely to get more of your transistors are going to be closer, are going to have a threshold voltage that is closer to the mean value of VT, which is great, right? As a designer, if you can't guarantee that all of the transistors will have the exact same VT, the best thing you could do is basically make this distribution as tight as possible. You want as much of your transistors as possible close to the mean value of VT. So your job, what you're trying to do is to reduce that spread and make that distribution tighter. And that's what we have done, right? If we quadruple the width in this example, the distribution becomes tighter around the mean. So that's great. And okay, so let's, oh, by the way, and so this is basically the same, this conclusion is the same as what we saw in Pelgrom's law, right? We said that if W by L, if you increase W by L product, then the variance will decrease. And so that's what we saw in this graph. If we increase the W by L product, then the variance decreases. All right, so next thing is that we are going to do another example. So let's assume for this example that the threshold voltage for a particular process, for a particular biasing condition and all, is 300 millivolts, okay? So after fabrication, you have these 5 transistors, and for the sake of an example, so M1 to M5, as shown here. And after fabrication, you start measuring the threshold voltage or of each one of those transistors. And you find out that, let's say, VT1 is 298 millivolts, so not exactly 300 millivolts. VT2 is 299, and VT3, by luck, it's like exactly 300 millivolts. So VT4 is something 2 millivolts higher, and VT5 is 1 millivolt higher. Okay, so now you can think of these 5 transistors. These are transistors in parallel, right? So you can imagine that this is equivalent to 1 big transistor with 5 times W over L, right? So that should be okay. But let's look at the threshold voltages. So if the threshold voltage of this 5 times W by L transistor is VT equivalent, so sorry. So VT equivalent, right? So then what is VT equivalent? It is VT1 plus VT2 plus VT3 plus VT4 plus VT5, the threshold voltage of the 5 transistors divided by 5. Okay, so let's start putting some numbers in. VT1 was 298 millivolts plus 299 millivolts plus 300 plus 302 plus 301 millivolts divided by 5. And what you would find out is that it's equal to 300 millivolts, which is the equivalent value, and it's also equal to what we were given in the process. But is that calculation right? Turns out it's not. This is totally wrong. We can't put numbers like this into the equation above. The reason is, and as we said earlier, these variables, VT1, VT2, VT3, VT4, these are random variables. And that's a very important thing to remember. You can't, as a random variable, and sorry, VT equivalent is also a random variable, okay? So as a random variable, you're not really interested in assigning values to these variables. When you talk about threshold voltage as a random variable, you're more interested in seeing the probability of that variable to have a certain value, right? So, normally you would say VT is 306 millivolts or 300 millivolts or whatever. Whenever you say VT, you're thinking of like a particular millivolt value, right? But when you talk about the threshold voltage VT as a random variable, you're more interested in seeing what is the probability that the threshold voltage is lower than, as an example, 300 millivolts. What is the probability that this random variable VT has a value that's higher than, let's say, 450 millivolts? Or what is the probability of VT to be in the range of 250 to 350 millivolts, right? So that's the kind of thing that we want to think about as a random variable when we're treating VT as a random variable. We are not assigning values to it. We are thinking about it in terms of probability and variation and standard deviation, that sort of thing. So So that's an important thing to remember. And so let's look at the circuit again, right? The same circuit, 5 transistors in parallel, equivalent to a bigger transistor with 5 times W by L. So this equation still stands, right? This equation is still true, provided like all of these are random variables, VT1, VT2, VT3, VT4, VT5, and VT equivalent. All of these are being treated as random variables, okay? And we can write this sum as a more concise form. But here's the most important part, and this is probably, if you were to take anything from this video, this is it. The variation of VT equivalent is the variation of any individual transistor divided by 5, or divided by any number of transistors that is that is there. So in this case, it's 5. So that's the most important part in this video. I'm gonna say, remember. And I mean, I don't mean like memorize, but I mean that this is an important equation for our whole discussion about random mismatches. So what we are trying to say in this equation is, let's say this VT1, right? It will have a certain variation. VT2 will have a certain variation. VT3 will have certain variation, VT4 and VT5. What this equation says is the variation in VT equivalent is going to be smaller than the variation in any one of these individual transistors. And that's like the main result that we're looking for. Essentially, what we're saying is that if we increase the size or the gate area of the transistor, then the variation is going to be lower, right? And yeah, that's basically what I've mentioned in the text below, that when we average 5 identical independent random variables, in this case, VT1, VT2, VT3, VT4, VT5, the variation of the average, which is sigma VT equivalent squared, is lower than the variation of the individual variables, which is sigma squared VT. Okay. And for larger transistors, like let's say 5 times W by L, the average variation is lower than the individual variation of any one of those 5 transistors. Okay, in this specific case. Another way to look at it is that, let's say if you have a group of, let's say you have a group of transistors that looks like this. So every transistor is like 5 times W by L. And you have another group of transistors that is W by L, so smaller transistors, and in the green you have bigger transistors, more gate area, right? And in the blue you have 4 times less gate area. So then the group in blue, these transistors will have a higher variance in the threshold voltage. In other words, the spread will be more damp. You will have more transistors that are away from the mean value of VT. In the group on the right, that is in the green, you have bigger transistors and more gate area. So, these transistors are more likely, the distribution of the threshold voltage for these transistors is going to be much tighter, and it's going to be closer to the mean value of VT. And so that's the takeaway. That's basically the Pelgrom law, right? Yeah, I've mentioned this again in some other words, but you can take a look at this text. Okay, so far we have talked about this amazing thing that if you beef up the transistor, you increase the the gate area, so the product of WL. If you increase that, then the variance in the threshold voltage would be lower, right? So is that a magic pill? Are there any downsides potentially to doing that? Let's look at it in terms of a current mirror design. So let's say you thought of like a current that you wanted to draw, and you thought of like a current mirror ratio, and then you set the W by L for a 2 transistor current mirror ratio. You've done the design, you've done the simulation, and you're seeing a certain current, whichever one you want, whatever value of current you want, you're seeing that in the simulation, and so you think you're done design. right, of a current mirror. And then you remember, okay, well, I watched part 3 of this current mirror video from us, and it talked about if you increase the gate area, then you're going to get lesser variation in the transistors of a current mirror. And so, if I want to reduce the error due to random mismatch, then I should beef up the transistors. Okay, so you say, okay, I'm gonna beef up both the transistors, increase the gate area for both the transistors, and then I will have less variation due to the threshold voltage and less random mismatch. But is there a downside? Are you paying a price? Well, first is obvious. You're paying a price in terms of layout area, right? Because you're making both the transistors bigger. But then also, when you make the transistors bigger, it's gonna draw more current, right? And so in practical industry design, when you work for a company, most likely one of the most important specs you're going to get from your manager, let's say, as an analog IC designer, would be the power consumption. And this is very common these days. We're trying to make lower and lower power analog circuits. And so when you're power constrained, you have a limit on like how big you can make your transistors and how much current you're going to sink through that current mirror branch, right? And so that's another thing. Also, if the current in the reference branch is fixed and you're increasing M1, which is the reference transistor, if the current is the same and you're making the transistor bigger and bigger and bigger, at one point it will go into triode. So that's another thing. You have to make sure that all the transistors in the current mirror are in saturation. And so that's also a limit in terms of like how much you can beef up the W by L. And finally, if you increase the size, again, we talked about bandwidth, right? The capacitances in these transistors would increase as you make the transistors bigger. And so the bandwidth would decrease. This current mirror would become slower. And so this might not be important if this is just a biasing current, but again, if this is a current mirror that's acting as an active load for a diff pair, let's say in an op-amp, and the current mirror is processing the small signals, then you need some small signal bandwidth. And you can't have very, 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 very big transistors that are very slow and they won't process the small signals that they're meant to process. Okay? So these are 2 or 3 or I guess 4 different downsides that you might want to be careful about, and there might be more. Right? So you can increase the gate area and you can get lower variance in the threshold voltage. You'll make more accurate current mirrors, lesser random mismatch, but at a certain price. Okay, finally, before I close this video, I want to talk about a final note here. So far, we talked about the threshold voltage and the variance of the threshold voltage. But if we go back to the start of the video, or start of the content, I said that it's not just VT, it's also beta. Beta also has a variance. Very similar idea. All the transistors are not going to have the same beta, and you're going to have a spread. And as it turns out, in Pelgrom's paper, Pelgrom's et al. Paper, the relationship for the variance of VT is very much similar. So you have, again, you have some constant, and this is the gate area. And that's the variance of beta. So this is very similar to, the VT equation that we talked about. So variance in threshold voltage is like AVT squared over W bar. So very similar, form of equation. So anyway, that's the variance equation for the threshold voltage and beta. And we started off the video, we discussed about the systematic mismatch, which is very much deterministic. We can, we know the causes, and if we eliminate those causes, then we pretty much suppress the systematic mismatch. Then the other kind is the random mismatch, and turns out that it's mostly because of beta and VT and also other things, but for now, beta and VT. And one of the things that we can do is the whole conclusion of this is, according to Pelgrom's law, if we increase the gate area, then we can reduce the threshold voltage, and we can reduce the variance. We can reduce the variance in the threshold voltage, and we can reduce the variance in the in beta as well. So that's pretty much it for this video. In the next video, we are going to discuss a little bit more about the Pelgrim's Law. We're going to talk about spacing and some other factors from Pelgrim's Law, and we're going to build up on our discussion in this part from this part. And then finally, we'll end up with some layout considerations for printers. But that's pretty much it for this video, and I'll see you in the next one. Bye-bye.